You know what really gets me going? When I see textbooks lying to students. Not deliberately, mind you, but through oversimplification that creates fundamental misconceptions. And there's one misconception in particular that drives me absolutely crazy. It's about electric current. Right now, as you're listening to me, you probably think you understand what's happening when electricity flows through a wire. You flip a switch and boom, the light turns on. Simple, right? Wrong. Completely, utterly, magnificently wrong. And I'm going to show you why what you've been taught is one of the most beautiful lies in physics. So let me ask you something. When you turn on a light switch, how fast do you think the electricity travels from the switch to the bulb? Speed of light? Close to it? That's what most people think. And here's where it gets interesting. They're both right and catastrophically wrong at the same time. How's that for a physics puzzle? Let me tell you the story we tell children. Actually, the story we tell most adults, too, and even some engineers who should know better. We say, electric current is the flow of electrons through a wire, like water flowing through a pipe. We draw nice little arrows, show electrons moving from the battery through the wire to the light bulb, and everyone nods happily. Case closed. But here's the problem, and I want you to really think about this. If current were actually like water flowing through a pipe, if you had to wait for electrons to physically travel from your light switch all the way to your light bulb, how long would that take? Let me give you the numbers, because numbers don't lie. The drift velocity of electrons in a typical copper wire carrying normal household current is about 1 millimeter per second. 1 millimeter per second. That's slower than a snail. That's slower than watching paint dry. That's so slow it's almost not moving at all. So if your light switch is 10 meters away from your light bulb and electrons travel at 1 millimeter per second, it would take about 10,000 seconds, or roughly 3 hours, for the first electron to arrive. 3 hours! But we both know the light turns on instantly. So what's going on here? This is the big misconception. People confuse the drift velocity of electrons with the speed at which electrical energy propagates. And this confusion, this fundamental misunderstanding, prevents people from really understanding what electricity is. Now, let me tell you what's actually happening. And I promise you, it's far more beautiful than this simple story. Imagine a pipe completely filled with water. Completely filled, from one end to the other. No gaps, no air bubbles. Now, if you push water in one end of this pipe, what happens at the other end? Does the water that comes out have to be the same water you pushed in? No. The water at the far end starts flowing almost immediately, doesn't it? Even though the individual water molecules you pushed might take minutes or hours to traverse the entire pipe. But here's where the analogy breaks down, because electricity is even more interesting than that. The wire isn't just a pipe, and the current isn't just electron flow. What's really happening involves electromagnetic fields, and those fields propagate at a significant fraction of the speed of light. When you close that switch, you're not sending electrons on a journey. You're creating an electromagnetic disturbance, a wave in the electric and magnetic fields that surround the wire. This disturbance, this wave, propagates along the wire at somewhere between 30 to 90% of the speed of light, depending on the wire's configuration and insulation. Think about that. The electromagnetic field changes propagate at roughly 200 million meters per second in a typical wire. That's why your light turns on instantly. It's not waiting for electrons to arrive, it's responding to a field change that travels at nearly the speed of light. But wait, there's more. And this is where it gets really interesting, where we get to the heart of the misconception. The electrons in your wire, and this is crucial, they're already there. All of them. The wire is packed full of free electrons, sitting there, waiting. When you close the switch, you're not injecting new electrons that have to travel from the battery. No, you're creating an electric field that causes all the electrons simultaneously to start drifting. It's like soldiers standing in formation. When the sergeant says, "Forward march," they all start moving at once. The sergeant's command, that's like the electromagnetic field. It propagates at the speed of sound. But the soldiers themselves, they march slowly. The command travels fast, the response is immediate everywhere, but the individual soldiers move slowly. Now here's something that really bothers people when I tell them. The energy that lights your bulb doesn't actually travel through the wire. It travels in the electromagnetic fields around the wire. The wire is just a guide, like railroad tracks guide a train. But the energy, the real energy, is in the fields in the space surrounding the wire. This is what the Poynting vector tells us. It points in the direction of electromagnetic energy flow, and that direction is perpendicular to both the electric and magnetic fields. In a wire carrying current, this energy flows in the space around the wire, not inside the conductor itself. The wire just provides the charges that create and respond to these fields. Now you might be thinking, okay, Feynman, this is interesting, but why should I care? The light still turns on, whether I understand this or not. And you'd be right, sort of. But here's why this matters. When you don't understand what's really happening, you can't make predictions in situations that are even slightly unusual. Let me give you an example. Suppose I have two very long wires, maybe 100,000 kilometers long, stretched out across space. I connect them to a battery at one end, and there's a light bulb between them just 1 meter away from the battery. When I close the switch, how long until the light turns on? If you think current is just electrons flowing, you're going to say it takes hours or days for electrons to travel through those long wires. But the actual answer? The light turns on in about 3 nanoseconds, the time it takes electromagnetic fields to propagate 1 meter at the speed of light. The length of the wires beyond that first meter barely matters for the initial turn-on. This isn't just theoretical. This understanding is absolutely critical for designing high-frequency circuits, antennas, transmission lines, computer processors, anything where signals propagate quickly. If engineers only thought about electron flow, modern electronics simply wouldn't work. They'd design everything wrong. Now, I should be honest with you. The complete mathematical description of what happens when you close that switch is incredibly complex. But let me give you the real numbers so you can see how different these two speeds really are. The actual drift velocity of electrons, how fast individual electrons move, depends on the current, the number of charge carriers in the wire, the cross-sectional area, and the electron charge. For typical household current in a copper wire, this gives us those tiny velocities like millimeters per second that I mentioned earlier. But the electromagnetic signal velocity in a transmission line, how fast the field disturbance travels, depends on the properties of the material surrounding the wire. In typical wires, this is around 60 to 90% of the speed of light. That's around 200 million meters per second. See the difference? These are completely different speeds describing completely different phenomena. One is measured in millimeters per second, the other in hundreds of millions of meters per second. They're not even in the same ballpark. They're not even playing the same sport. Let me address some questions students always ask me. Professor Feynman, if electrons move so slowly, how can I send information quickly through a wire? You're not sending electrons, You're sending a pattern, a wave in the electromagnetic field. It's like pushing a line of shopping carts. Push the first one and the last one moves almost immediately, even though no single cart traveled the whole distance. But aren't the electrons carrying the energy? This is tricky. Yes, moving electrons have kinetic energy, but that's not the energy that powers your light bulb. The energy comes from the electromagnetic field. The electrons are like mediators. They respond to the field and create fields themselves. And this interaction is what transfers energy from the source to the load. What about a C current? Does this change anything? Oh, a C makes it even clearer. In alternating current, electrons just wiggle back and forth, maybe moving a tiny distance in each direction. They go nowhere on average. Yet you can transmit enormous amounts of power over long distances with a C. How? Because the electromagnetic fields carry the energy, not the electron motion itself. If the energy travels in the fields around the wire, why do we need thick wires for high power? Excellent question. The thickness of the wire determines how much current it can carry without overheating. Remember, the electrons are drifting through the wire, colliding with atoms, creating heat. More current means more collisions, more heat. The electromagnetic fields carry the energy, but the wire still has to handle the current, and that creates practical limitations based on heating. So here's what I want you to take away from this. When we teach that current is the flow of electrons, we're not technically wrong, but we're missing the deeper, more beautiful truth. Current, the actual measurement we call current, measured in amperes, is indeed the rate of charge flow past a point. That's the definition, and it's correct. But the phenomenon we call electricity, the thing that carries energy and information, the thing that makes your lights turn on instantly, that's not just electron flow. That's an electromagnetic phenomenon involving fields propagating through space at nearly the speed of light. The electrons do drift slowly, that's real, but that drift is a response to the field, not the cause of the rapid energy transfer. The field comes first, propagating quickly, and the electrons respond to it, moving slowly. Both things are happening simultaneously, but they're different phenomena with different speeds and different roles. This is what I mean when I say physics has layers. The simple story isn't wrong, it's incomplete. And when you dig deeper, when you look at what's really happening, you find something far more subtle, far more interesting, and ultimately far more useful than the simple story. Think about it this way. When you understand that electrical energy propagates in the electromagnetic fields around wires, suddenly everything makes more sense. You understand why transmission lines are designed the way they are. You understand why the spacing between wires matters. You understand why high-frequency signals behave differently than low-frequency ones. You understand antenna theory, waveguides, and countless other phenomena that seem mysterious if you only think about electron flow. Let me leave you with one more thought experiment that really drives this home. Imagine I have a giant loop of wire, maybe millions of kilometers in circumference, out in space. I put a battery in this loop. Now, when I connect the battery, how long does it take for the current to start flowing everywhere in the loop? If you're thinking about electrons traveling, you'd say it takes a long time. The time for electrons to physically traverse millions of kilometers at millimeters per second. That would be many years. But that's not what happens. When you connect the battery, an electromagnetic wave launches from the battery and propagates around the loop at nearly the speed of light. Within seconds, the electromagnetic field has propagated around the entire loop, and electrons everywhere in the loop start drifting simultaneously. The current is established throughout the entire loop in the time it takes light to travel that distance, not the time it takes electrons to drift that distance. This is the power of understanding the real physics. The simple model, electrons flowing like water, would give you completely wrong predictions for this situation. But when you understand electromagnetic field propagation, everything makes perfect sense. You know what bothers me most about misconceptions in physics? It's not that people don't know the detailed mathematics. That's okay. Not everyone needs to be able to write down and solve complex equations. What bothers me is when people think they understand something, but they're actually working with a cartoon version that will lead them astray when it matters. The big misconception about current, thinking it's all about electrons physically traveling from source to load, is exactly this kind of cartoon. It works fine for very simple situations, but it completely fails to explain why lights turn on instantly, how high-frequency circuits work, or where the energy in an electrical system actually resides. Real understanding means being able to predict what happens in new situations. It means knowing not just a simple description, but what's really happening in nature. It means understanding that when you flip a switch, you're launching an electromagnetic wave, not sending electrons on a journey. And here's the beautiful part. Once you understand this, once you really get it, you start seeing the world differently. You realize that empty space isn't empty. It's full of electromagnetic fields carrying energy. You realize that wires are just guides for these fields, not pipes for electron flow. You realize that almost everything about modern technology, from your smartphone to power grids to satellite communications, depends on this understanding of electromagnetic field propagation. So the next time someone tells you that electricity flows like water in a pipe, you can smile knowingly and say, well, that's not quite the whole story. And if they want to know more, you can tell them about electromagnetic fields, about signal propagation, about the difference between drift velocity and wave velocity. You can tell them that the energy doesn't actually travel through the wire, it travels around the wire in the electromagnetic fields. Because that's what physics is really about, not memorizing simple stories, but understanding the beautiful, complex, fascinating reality underneath. And reality, I promise you, is always more interesting than the simple story. It's richer, more surprising, more useful, and ultimately more satisfying when you take the time to really understand it. The misconception about current isn't just a small error. It's a doorway. On one side is a simple, comfortable, but ultimately limiting view of electricity. On the other side is the real electromagnetic universe, where fields propagate at light speed, where energy flows through empty space, where the same principles that make your lights work also explain radio, television, radar, and the very nature of light itself. I hope today I've helped you step through that doorway. I hope you'll never look at a light switch quite the same way again. And I hope you'll remember that in physics, the truth is always more wonderful than the simplification. Thank you.